Hello, welcome to our course on advanced quantum mechanics. Who am I? My name is Achim Kempf. You can call me Achim. Short biography. I was born in Germany. This is also where I did all of my studies. I did my PhD at the University of Munich. And then I was a postdoctoral researcher in the UK, and then in the United States, and I have then become a prof in Canada. My research is in mathematical physics. Mostly I study the physics of information, and I apply that to cosmology, quantum gravity, relativistic quantum information, and more recently, quantum machine learning. Actually, I'm very proud that some of my students, together with Google, developed what is called TensorFlow Quantum. This is a software package that combines Google's software for machine learning, TensorFlow, with Google's software for programming quantum computers, which is called Cirq. And so TensorFlow Quantum is what could be very useful if one day you want to do machine learning on quantum computers. Two of my students have been hired by Google recently, and one of the students involved in that project is Evan Peters, who is one of our TAs. So if you have any questions about quantum machine learning, he's your guy. Our other TA is Basil. Basil is a brand new master student. Now, our course, Advanced Quantum Theory, is meant to prepare for the topics that I just mentioned. So, physics of information, quantum cosmology, quantum gravity, relativistic quantum information, quantum machine learning, and so on. For these topics, you usually don't get anywhere if all you know is the Schrödinger equation. For that, you need to understand quantum mechanics more deeply for quantum information, and for example, then to upgrade things to quantum field theory. So to prepare for all of these advanced topics that you can do in grad studies, the aim here in this course is to show how any quantum theory works, not just the non-relativistic Schrödinger equation. Of course, we will mostly apply what we do to non-relativistic quantum mechanics, but the framework that we will develop is much more general. And it's the same framework, for example, for quantum electrodynamics or any other quantum field theory. So, what this means is that I'm not going to rely on the fact that you've seen the Schrödinger equation and solved the Schrödinger equation before. Instead of following up on the Schrödinger equation, we will start afresh. We will start completely afresh, study the origins of quantum mechanics, and then the Schrödinger equation will just pop out at some point. You see, when I was an undergrad student studying quantum mechanics, in my course, the Schrödinger equation just fell from the sky. At the very beginning of the course, we were told, this is the Schrödinger equation, let's solve it. And I thought, what the heck? The Schrödinger equation looks nothing like Newton's laws. And yet, both of them are supposed to describe how a rock falls into water. You see, Newton's equations can describe the trajectory of a rock when you throw it. But Schrödinger's equation is supposed to be able to do that too. After all, it's supposed to describe electrons, protons, atoms, molecules, rocks, water, all of it. So how come the Schrödinger equation can describe what Newton's equations describe, and yet the Schrödinger equation is so completely different structurally? I found it pretty unsatisfactory. And in fact, you do need a deeper understanding of these things in order to then go on to do modern work on quantum mechanical and quantum theoretical problems. So at the beginning of this course, we will be concerned with the origins of quantum mechanics. Now, quantum mechanics has historical origins and it has logical origins. The historical origins of quantum mechanics I've written up for you in the first part of the lecture notes that I already put on the web. I very much encourage you to read these historical origins. Also because the history of the discovery of quantum mechanics is extraordinary. And it shows how, well, how discoveries of a fundamental nature are being made or have been made. And this may inform us about what it takes to make similar progress in the future. Nevertheless, it would go too far to discuss the history of quantum mechanics. So I just wrote it up for you. Please do read it. But what we will be concerned with here at the beginning of this course is what are the logical origins of quantum mechanics? Where does this all come from? How is it related to classical mechanics? How can it be that quantum mechanics describes the same as classical mechanics, just better, even though the structure looks so different? Schrödinger equation looks so different from F equal ma, for example. Okay, now before we go into the actual material, let me mention a few logistic points. Very important is that you keep regularly checking our course homepage. You must have found the homepage because otherwise you wouldn't have found this video. Okay, so our course homepage, which is part of my groups, of my labs pages, so our course homepage will be updated all the time. So if there's any news about deadlines for homework or how we will do the midterm and the final, which I don't know yet, all of this information will continually be updated on the homepage of the course. On the homepage of the course are also links to the various other platforms that we use in this course. In particular, Piazza for an online discussion forum. We use Crowdmark for the homework. Now, if regarding the marking, you have any questions, partial credit or incorrect counting or whatever it might be, then please email both TAs, Evan and Basil, and then the TA who actually graded your work will reply to you. Evan and Basil, our two TAs, will also do tutorials. They will be live online. I realize that some of you may not be able to take part all the time in those live tutorials. So we will try our best to record them and put them on the web for you. I also will offer office hours every Friday morning, and that will start along with the tutorials that will start next week. Okay, let us get started. Chapter 2. Remember, chapter 1 was the historical introduction, the historical origins of quantum mechanics. So, chapter 2. The first message that I want to get across here is that the discrepancy between Newton's description of a rock flying into a lake and quantum mechanics description of a rock flying into a lake are indeed very different. This is not just apparent, this is really a fundamental difference. In other words, Newton's laws of classical mechanics cannot be upgraded as they are to obtain quantum mechanics. See, when experimentalists had found out that Planck's constant must play in a huge role in these new upgraded laws of physics about 100 years ago, they had very little to go by. So, of course, they tried simple things. We don't hear about this now because they were not successful, but they did, of course, try simple things. They said, okay, we have Newton's laws, for example, F equal ma, or F equal mx double dot, and then how can we improve that to get a quantum version such that it describes nature better? Well, a simple idea might have been to try to modify it like this: F equal to m x double dot, same as a, and then let's say plus h. If h is a small number, maybe if we just overlooked it and so on. Now, that attempt, of course, doesn't work. We can see that already on the basis of the units. The units don't match. Planck's constant has the units of an action, but F has the units of a force, and so does mx double dot. So that cannot be right. No way. If you want to improve over classical mechanics, over Newton's mechanics, to obtain quantum mechanics, then you might then in desperation think, all right, maybe I should try something like this. Mx double dot times 1 plus h over xp. See, the units would match now because the product of x and p also has the units of an action. But nah, that's not going to be right either. You can tell without trying, because if x is small or p is small for small positions close to the origin of the coordinate system or small momenta, small velocities, this term would blow up and we would have known about it. So that's not right either. You can try then perhaps f equal to mx double dot 1 plus xp over h. Maybe this does the trick and we suddenly get quantum physics. Of course it doesn't, because h is a tiny number. This expression would be huge. So that doesn't work either. You can show that none of this would work. This is just not a way to go and improve Newton's mechanics to obtain quantum mechanics. There was this enormous insight by Dirac, and he was the first to really understand how quantum mechanics relates to classical mechanics. Heisenberg and then Schrödinger had written down the Schrödinger equation and the Heisenberg equation, but they hadn't understood really where it came from. And Dirac did. He was the first. And Dirac did it by remembering that classical mechanics had been formulated on a higher level after Newton. There were people like Hamilton and Lagrange who figured out a better description of classical mechanics. It was still Newton's classical mechanics, but it was a more sophisticated way of writing it. And Dirac remembered that, and he thought, aha, let's try that. Instead of trying F equal ma, let's try to write down the classical laws of physics, especially of classical mechanics. But Dirac's method also works on electrodynamics and other things. So Dirac said, let's try to write down classical mechanics, not in Newton's way, but in the more abstract way of Hamilton. And indeed, he then succeeded. And he found how Hamilton's formulation of classical mechanics can be fixed by just putting an h at the right place, just as putting Planck's constant at the right place. And that helps us a lot, understanding that quantum mechanics and classical mechanics are really very similar, apart from the introduction of this h in the right place. Very similar, and that's why quantum mechanics really supersedes classical mechanics. So Dirac's insight was, must start from Hamilton's more abstract formulation of classical mechanics. Now, what do we mean by abstract? I mean something very concrete. Namely, levels of abstraction. Consider Newton's formulation of classical mechanics. What level of abstraction had Newton achieved? Well, Newton had this. Newton had F equal mx double dot, which is a differential equation. I mean, you understand that when I write F equal mx double dot, that's the simplest case. Newton can, of course, describe very complicated machinery, very complicated mechanical circumstances, but this is at the heart of it. And in complicated circumstances, you might just get several coupled differential equations. But if you work with Newton, this is your starting point. You look at the situation that you want to describe, and then you use Newton's laws, all of them, including the gravitational law, F equal ma, and action is equal to back reaction up to a sign. You get differential equations. They are at a pretty high level of abstraction in the following sense. If you take differential equations and you solve them, like this differential equation, you get as the solution to your problem a function. Actually, I should put this elsewhere. Here. Whenever you take a differential equation, you solve it, what you get is a function. The solution to a differential equation is a function. But then a function can be solved for a variable, and then that variable eventually takes on some value, which is some number, which is something that you can measure. If you remember back to your education in mathematics, the very first things you learned were numbers, just counting. And then at some point, variables were introduced. And this at the time probably felt quite abstract. And some kids struggle with this for a while. How can a letter stand for numbers? Well, it's more abstract because the letter could stand for any number. And then at some point in your mathematical education, you got presented with the next level of sophistication or the next level of abstraction, which is functions, which you can then solve, or equations that involve functions, you can then solve for variables. So you can describe much more. So just like a number describes one thing, a variable can describe lots of values. A function can describe lots of relationships between these variables. And then eventually, as you transitioned into university, you learned about differential equations, whose solutions are functions, right? Whose solutions are variables, which then can be solved for numbers. So you see there's a hierarchy of abstraction going on, and Newton's level was differential equations. But even before the advent of quantum mechanics, physicists had looked at this hierarchy of abstractions and thought, can we do better than this? Is there a way to derive the differential equations? Now you may wonder, why would you want to derive that again? You already have F equal mx double dot. Well, remember, the situations can be very complicated. Let's say you have multiple objects that have multiple forces with which they act on each other, with various constraints and so on. Then, just to even set up the differential equations, which are ultimately Newton's equations, but because of the complications of the setup, it might be actually quite difficult to write down these differential equations. So people like Hamilton thought, maybe there's a simpler way. Maybe we can derive the differential equations from something more abstract. That could be very useful. So the question that Hamilton asked is, could it be that there's a higher level of abstraction where from you can then derive differential equations from which you can get the functions, the variables, and eventually the number value predictions for experimental outcomes? And the answer is yes. And let's call it Hamilton's principle. And this is the principle on which Dirac operated. He had noticed, of course, that Newton's equations on this level, the differential equation level, looked nothing like the Schrödinger equation or any other formulation of quantum mechanics. But classical mechanics in Hamilton's formulation, that looked like quantum mechanics. And there was an easy transition from one to the other. And the similarities and differences became very clear. For completeness, I should say that while in this course, we will do it this way, we will follow Dirac. By the way, here's the book, one of the most famous books of physics, Dirac's book of Principles of Quantum Mechanics, where he explains all of these things that I'm telling you now. While we will follow Dirac for most of the course, there is another way. Because Hamilton was not the only one who found a way to derive classical mechanics or to derive Newton's level, the differential equations, from a higher principle. Hamilton's principle is not, Hamilton's formulation is not the only one. There is also Lagrange's formulation. And it turns out from there, you can also get to quantum mechanics. But it doesn't look like the Schrödinger equation or the Heisenberg equations. If you start with Lagrange's formalism at the higher level, higher than differential equations, then you end up with Feynman's quantum mechanics, with Feynman's formulation of the path integral. We will cover that eventually too, but mostly we will follow here Hamilton's principle and Dirac's approach. Okay. Before I forget, you may be wondering, is there anything above that? Like here? Could there be something from which we can derive the Hamilton principle? From which we can then get the differential equations, the functions, the variables, and then the predicted numbers. There is. We will get to it later in the course. It's basically symmetry principles. And then the big question is, where do those symmetries come from? And that's pretty much where we are now. Okay. But before we can go more steps up in this hierarchy of abstraction, let's figure out what this is. Remember what the challenge is. If we have a complicated contraption of multiple, let's say, point masses, and they are connected to each other with various springs and bells and whistles, then it is possible to use Newton's laws to write down the various equations that they hold, but you need to draw diagrams with forces and force parallelograms and things like that. This is what motivated Hamilton to try to simplify things. And what he came up with is the idea or the observation that actually all you need to know at this top level above the differential equations is, and I'm filling it now in, is the energy. It's the energy, which is also called the Hamiltonian. This is both easy and extraordinary. You see, what Hamilton discovered is that instead of deriving Newton's differential equations for a complicated system, you can simply write down the total energy of the system, which is not hard. You just sum up all the potential energies and all the kinetic energies. You don't need to draw any force diagrams for that. You just sum up all the energies of the system, then call this total energy the Hamiltonian. And this expression, the expression for the total energy of the system, in fact contains all information about the structure of the system, and therefore can be used to derive the equations of motion of the system, the differential equations, the ones that Newton would also have written down, except you didn't have to draw any force diagrams. You only needed to write down the sum of the kinetic and the potential energies. So what was the challenge that Hamilton faced in order to prove what he wanted to prove here? Simplest example. Let's say a harmonic oscillator. There, our energy function, the total energy of the harmonic oscillator, let's call it H for Hamilton, is equal to p squared divided by 2m plus some spring constant half x squared. This is a 2. Now, this is the total energy. From that total energy expression, Hamilton wanted to derive the differential equations that Newton would have written down. And they are that x dot time derivative of x is equal to p divided by m. And another differential equation, namely that p dot is equal to minus k x. So you see the challenge that Hamilton faced here is to invent a procedure that would get you from the Hamiltonian to this bunch of differential equations. So it's a procedure where you plug in an expression in the x and the p's, and out pops a bunch of differential equations. In this case, it's going to be relatively simple, but remember, this is supposed to work also for complicated contraptions. And in quantum mechanics, this could be molecules that we use for quantum computing or quantum field theories, complicated things. So Hamilton had to invent a method to go, Hamilton and others, had to invent a method that would take as input an expression like h and would give us output a bunch of differential equations. What is that procedure? What is that central tool that we need there? And what we need here is, what is this? Need the Poisson bracket. And the Poisson bracket is usually written with curly brackets. You may wonder, do we really have to get into this? This is classical mechanics after all. We do. In quantum mechanics, all that we do here now with the step from energy to differential equations, the Poisson brackets, are going to be the same. Not similar, the same, identical. So it will be worth studying what this business is with the Poisson brackets and how the mathematical tool of Poisson brackets can be used to get us from an expression of the total energy to the Newton's equations of motion for the dynamics. So we have two questions here. First, how is the Poisson bracket defined? How does it operate, right? How do we actually use it? And secondly, how is it employed to derive from the total energy expression, the so-called Hamiltonian, what the equations of motion are? So to the first point, what's the Poisson bracket? The Poisson bracket is a multiplication. It multiplies two polynomials, and out you get the result of this multiplication is another polynomial. So it's a multiplication of polynomials. That's the tool that you will need. So let's say we take polynomial 1 is, let's say, minus 2 p1, p1 being, let's say, the momentum in the first direction. And then let's say the second polynomial could be 3x1 squared plus 7p3 to the fourth minus 2x2 to the third p1 to the third plus 6. Up, 6. So we have two polynomials here in the variables that occur in physical systems. What's their product? What's their product under the multiplication, which is called Poisson bracket? The answer is their Poisson product is, and here we use the notation of the so-called Poisson bracket. You write the two polynomials that you want to multiply in the Poisson way. 3x1 squared plus 7p3 to the fourth minus 2x2 to the third p1 to the third plus 6. And then there will be rules according to which you can evaluate what that product is, and the output, the end result of that product, is another polynomial. In this case, the outcome is 12x1. Now, that may not be obvious to you yet, I hope anyway, that it's not so obvious just yet. But that's overall the structure. You plug in two polynomials and you get out the polynomial. So what are the rules? Why? Well, there are two sets of rules for the Poisson bracket that define the Poisson bracket. First set of rules. By definition, we have that if xi is the position of some degree of freedom, some particle, and pj is the momentum of some particle in some direction, then the Poisson bracket of these two, viewed as polynomials, is by definition delta ij. Recall the Kronecker delta, delta ij, is equal to 1 if I equal j, is equal to 0 if I not equal to j. Right, so by definition, we have that this is true. We have that xi, xj is equal to 0, and pi, pj is equal to 0. And all of that for all I, j. Obviously, that's not enough to evaluate the Poisson bracket of two polynomials, because polynomials have powers in x and p that are higher than 1. So far, we only have the outcome of the Poisson multiplication of the basic variables, the positions and the momenta. So there are additional rules. And these rules will allow us to evaluate the Poisson bracket also for arbitrary polynomials of arbitrary degree. And they will, these additional rules allow us to evaluate the Poisson brackets for arbitrary polynomials because they allow us to reduce these products to these basic cases where it's just x and p's that get multiplied to each other. So what are they? These other rules, the second set of rules, are that if f is some polynomial in the x and the p's, g is some polynomial in the x and the g's, and the x and the p's, then this is antisymmetric, whatever the outcome of the multiplication is, it has to obey that rule. So this is anti-symmetry. Another rule is that if C is an arbitrary number, then CF multiplied with G is equal to C times the Poisson multiplication of F and G. This is linearity. This also holds true if the number is multiplied on the G. Obviously, we can prove that by using the first equation, just swapping the two and picking up a minus sign. There are more rules. There's also the rule that we have additivity. So we have that the Poisson bracket of a polynomial f with a polynomial g plus a polynomial h is equal to the Poisson bracket of f with g plus the Poisson bracket of f with h. This additivity and we finally also have that the Poisson bracket of a polynomial f with the product of two polynomials, g and h, is equal to the Poisson bracket of f with g times h plus g times the Poisson bracket of f with h. This is the product rule. Cool. Difficult to write here. You can tell that this rule is going to be very important because it allows us to decompose the product of polynomials into sums of products of polynomials of lower degree. Because GH might be a complicated polynomial of high degree, but we can write it as a product of two polynomials and then use this product rule to write it in this form here on the right-hand side, which is only containing polynomials of lower degree. So we can iterate this and eventually get just the Poisson bracket of x and p's. By the way, this is called the product rule, and you may wonder, what? I've heard that name before. Product rule, isn't that something to do with the derivative? Isn't that the Leibniz rule? Well, it is. And it turns out that the origin of that particular rule for the Poisson bracket is the product rule. It's the Leibniz rule. It has to do with the fact that the time derivative obeys the Leibniz rule, the product rule for differentiation. Ultimately, this expression here, this rule for the Poisson brackets, is expressing the differentiation. For now, let's just list these rules for the Poisson brackets. Piece by piece, it will become clearer why they had to be chosen in exactly the way that we have them here. They are tailor-made for classical mechanics. But in fact, they also work not just for classical mechanics of point particles. They also work for the degrees of freedom of fields, such as the electric field, magnetic field, strong force field, weak force fields, fermion fields like electron fields, and so on. In this case, the x and the p's will be replaced by the amplitudes of the fields and the time derivatives of the amplitudes of the fields. The amplitudes of fields and their time derivatives, and we will see this theme recur in this course, form a pair, just like positions and momenta do, because the momenta are essentially also just the time derivatives of the positions. Okay, so these Poisson bracket methods can also be applied to fields, classical fields, and then quantum fields. Right, there's one more rule that we need to list here, and that is that f with gh plus, and then we cyclically commute this, so we have the h now, and then we have fg plus, and then we cyclically permute so that we now have the g in front, and then we have h comma f. This is equal to 0. And that's called the Jacobi identity. Okay, if you've studied Lie groups, then you know that Jacobi identity comes up in Lie algebras. So let's do an example now. For example, we take x3, p3 squared. What might that be? Let's see. We can use here the product rule to break this down into something that's linear. Namely, we can write this as x3, p3, p3. But you see, now it's of the form f, gh. So by the product rule, what we obtain is that this is equal to the Poisson bracket of x3 with p3 plus, and then it is the same thing again. So it's p3, x3, p3, almost the same thing, right? Except that one of the p3s is to the right, and the other case it's to the left. Now, if we go back to what we had earlier about the linear polynomials Poisson bracket, we see what they are. So here, x3 Poisson bracket with p3 is delta of 3, 3, which is 1. So what you obtain is that this is 1, that is 1, and therefore this is simply 2p3. Okay, so now we've evaluated our first example of the product of the Poisson product of two polynomials, and the Poisson product of two polynomials that I showed at the very beginning, you should now be able to evaluate, namely this one, right, where I claimed that it's 12x1. It will be part of the homework. For completeness, I should also mention how this generalizes when we have multiple particles around. So let's say we have many particles. Each particle has positions x1, x2, x3, but it's also one of many particles. And which particle it is, we will write here as a superscript, r. So it means it's the rth particle. And this expression here is the ith position variable of the rth particle. And then we take the jth momentum of the s particle. Then their Poisson bracket is going to be only 1 if this position belongs to that momentum. So the I and the J have to match, but also they have to belong to the same particle. So we have this Poisson bracket. And then All of the positions have a zero Poisson bracket with each other, and so do the momenta. Okay. So, what is the general structure of all of this? The structure is the general mathematical structure that we have just described here is the structure of a set of polynomials in all of the x's, all of the p's, of all of the particles that are involved here. And let's collect what we can do with these polynomials now. As usual, we can add polynomials in x and p. We can multiply polynomials in x and p, but we can now also Poisson multiply polynomials in x and p. A structure like that, where we have additivity as in a vector space, namely polynomials can be added with prefactors, so they form a vector space. And we have the ordinary multiplication of polynomials on top of the Poisson multiplication. Such a structure has a name. It's a Poisson algebra. A Poisson algebra is a vector space, in this case of polynomials, that has two kinds of multiplication. One kind of multiplication is the usual associative kind. That would be just the ordinary multiplication of two polynomials. And we allow ourselves to do this here, of course. And the Poisson algebra requires also a second kind of multiplication. That's the kind of multiplication that the Poisson bracket provides. And the axioms of such a Poisson bracket are the axioms of the second set of these axioms here, are the axioms of a Lie algebra. So technically speaking, a Poisson algebra is both an associative algebra and a Lie algebra. And there are to be consistency conditions between the two. And these consistency conditions we listed here. Here, the product rule. The product rule is relating the multiplication, here the associative multiplication that comes up here, the G and the H. Let me just underline it in case you can't see my cursor. This is an associative multiplication. And the rest of all of this here is, of course, the Poisson multiplication with the Poisson bracket, and that's not associative. So this is the central axiom that relates the associative to the Lie multiplication. In any case, it will be part of the homework to look up what these axioms are so that you are becoming familiar with what it is on the mathematical level that we are dealing with. So this is the structure of a Poisson algebra. Poisson algebra, which is associative algebra, and a Lie algebra, and a consistency condition between them. This is more for the mostly mathematically inclined among you. But why did we do all of this? Why did we do these complicated axioms here? What's the purpose of it? Let's remember what it's for. It's meant to be a mathematical machinery, or used as a mathematical tool in order to get us from Hamiltonians on the very top level of abstraction here, from the Hamiltonians to the differential equations. Somehow, given the total energy of a complicated system, such as molecules used for quantum computing or something, somehow from the total energy expression, the Hamiltonian, the Poisson brackets give us a means to derive all the equations of motion, all the differential equations that need to be solved, so that we get from the top level of abstraction, the energy, the Hamiltonian, down to the differential equations level. And from there we know, right? We know how to solve differential equations to get functions, which we can solve for variables, and then eventually get numbers. So you may ask, well, how do you do it? How do you get from the Hamiltonian to the differential equations? And I will give you here a brief preview of this. So we have here the Hamiltonian. And down here we have the differential equations. Differential equations of motion. And this derivation step is using the Poisson bracket. And how does it do it? Well, we have the Hamiltonian H, which is a function of all of the x's and all of the p's. Well, let's write x1, boop, 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 xn, p1, pn, all of them. The Hamiltonian is some expression in the positions and the momenta, right? And then the differential equations that we get, and we get one differential equation for each variable. There's going to be a differential equation for x and a differential equation for p. One for x1, one for p1, one for x2, one for p2, etc. And how does it look like? Well, if f is any polynomial, then what we have is that df by dt is equal to the Poisson bracket between that polynomial of f and the Hamiltonian. I'm suppressing the dependencies here, plus df by dt. What exactly that means, why there is this extra df by dt, we will cover next time. But for now, let's just look already at what that solution is of Hamilton. Hamilton said, this is true for all polynomials f of all of the x's and all of the p's. I won't write it all out in terms of x1 to xn and p1 to pn, such as f equal to x1, f equal to p1, etc. So what you need to do in order to find out what the equations of motion are, according to Hamilton, is to pick the variable of which you want to know what the equation of motion is. And that variable could be just x1 or p1, or it could in fact be any polynomial of x1 and p1. And then in order to get the time derivative, or then the time derivative of that expression that you chose, that time derivative is going to be given by this polynomial, right? F is a polynomial, H is a polynomial. Oh, I don't know if you see my cursor, right? So this is a polynomial because F is a polynomial, H is a polynomial, F is a polynomial. So overall, all of this is a differential equation because here's the time derivative and here's just a polynomial in the x and the p's. Okay, so this was Hamilton's insight that classical mechanics can be formulated in this way. You simply write down the sum of all the kinetic energies and all the potential energies. This is what the Hamiltonian is. It's the total energy of the system. And then use the rules of the Poisson brackets in order to write down these equations for all the variables. So F needs to be chosen to be x1, x2, x3, x4, whatever comes up, p1, p2, p3, p4. And then for each of these choices of F, you get a differential equation here. The collection of all of them is the equations of motion that need to be solved. Now you may wonder, okay, we set out to go from classical mechanics to quantum mechanics. And I showed you that you can't just take Newton's equation and add an h somewhere and suddenly it becomes quantum mechanics. So you may wonder, how about here? At this point, can we introduce h somewhere so that what we describe here becomes quantum mechanics? No, it's way cooler than this. What I showed you today, I showed you for classical mechanics, right? But it's exactly the same in quantum mechanics. There is no h, there is no difference at all. Everything we did today is still true in quantum mechanics. Where h comes in, we will see soon. But so far, the structure of classical mechanics is the same as that of quantum mechanics. Okay, so that's it for today.